Volumes by cross sections is probably one of the hardest volume type of problems to visualize. People have a hard time with it. I had a really hard time with it for a long time. So I'm going to try and make it easier here and show you an example. And right now on the screen we're just looking at a graph with an XY axis and a circle on it basically. And the way volumes by cross sections works is the strategy is it's a stacking problem. It's different. We're not doing any revolving. The last couple of methods we've learned are disk and washer, and those are all about spinning a graph around and making an object. Instead, what we're going to do is we're going to take the graph on the screen and kind of picture dropping it flat. And I'll show you what that looks like. In fact, I'm going to draw a bunch of chords across this circle. And all it is a bunch of straight lines that I'm drawing. And then I'm going to take the graph and lie it down flat. So picture it as totally a flat graph. Instead of spinning, what I'll do is I'll stack a bunch of objects inside of this circle. So for this example, I'm going to stack squares because they're easy to see. So check out what I've done is I've got a bunch of different squares stacked in here. Here's a little black square. Here's a little bit of a bigger one, and then the purple and the pink one get bigger and bigger. The squares, the size of the square are being determined by the circle. So I'm connecting one end of the circle to the other end, one end of the circle to the other end. And so they're getting from small ends to bigger and bigger and bigger and bigger. And if I stack enough of those, watch what this is going to look like. And I can rotate this. Like, remember, we're looking straight at this graph. It's those chords that I drew that are the squares. So I'm going to sweep a square. Watch this. Here's a square. Well, multiple squares. It's getting bigger and bigger and bigger as the circle gets bigger. So here the square is getting actually quite large. Then it's going to start getting a little bit smaller and smaller as the circle's kind of tying off at the end here. And basically the idea is if I could stack infinitely many small of these squares in the middle here, it would create a solid, and it would end up creating a solid like this. Watch this. Here's all the squares being stacked and stuck together so that a solid shape forms. You can kind of watch on the screen like as the squares are forming, the shape is forming. And I want to find the volume of this solid is what I want to end up doing. So check it out. You can see the shape. It's a really interesting shape. Well, okay, I think it's interesting. Here's the shape overall. So remember those 4 squares I had drawn earlier? Well, here's those 4 squares. They're still inside of this shape. I can hide them or make them show up. What we're basically going to do is add up the volume of all these squares. That's the game plan. Add up the volume of all these squares. And if I rotate this back, you really can't see what this looks like when it's straight at it. But when we move it and make it flat, that's when we can see the object. So, volumes by cross sections. The things you need to know is you probably should watch the other 2 videos on this to really get it down. But the idea is we're going to add up all the shapes. Now, I stack squares. I could have changed my mind. I could have reset this and tried to set triangles inside of the circle, or semicircles, or rectangles, or I could do lots of different shapes. So I guess the note that I'm going to write on here, let's see. Let's drop the y-axis again flat. And then let's write a little note here. Make sure you're kind of getting the hang of this. So here's what I'm going to write. The concept is we're stacking a shape. So I'm going to stack a square here. There's my square. Not a very good looking square, but it's a square. It's a stacking method. And what we're basically doing is adding up the stacks, adding up each slice. And so to get the volume of a slice, we have to take the area of the front of it and times it by the thickness. That's the concept. So we're going to take area times the thickness to get our volume, which is basically what we do when we revolve. Like, we take the area of a disk and then we times it by the infinitely skinny thickness that it has. So same concept. I'm going to wipe this out again. Let's write on the screen here that the volume is going to equal an integral where we add up all the areas of every single one of the squares times the thickness. Well, the thickness, we're going to make these squares so thin that you can't really give it a thickness number. Like the width is going to be infinitely small. So we'll call it delta x. And really the bulk of the work for these problems is figuring out what to write for an equation for area. And that's going to depend on the graph. We picked for this visual example, we picked this circle here just because it seemed like a good choice. But we could have graphed anything. I could have graphed f of x equals a parabola, x squared, or x cubed, or whatever I feel like, and try and stack some shapes in the middle of that function. So hopefully you kind of got an idea for the visual. Watch the other two videos because this is definitely a little bit of a harder topic to understand, and hopefully it helps. I'll see you guys in class.